In this video, we'll guide you through the step-by-step process of draft survey calculations. We'll cover the entire procedure, starting with draft corrections, calculating the amount of cargo already loaded on board, and all the way to determining the remaining cargo to be loaded. Let's begin by walking through our scenario, where we calculate the amount of cargo already loaded on board, based on the vessel's present draft. Then determine the remaining cargo to be loaded, as per the charterer's instruction to load 32,000 metric tons of dry bulk cargo. The ship will be loading in dock water with a relative density of 1.017. To begin the draft survey calculations, we'll need to gather the following data. We'll go through each of these given data step by step, starting with the observed drafts taken from the 6 points of the vessel. The first step is to calculate the mean draft forward, aft, and midship. The formulas are as follows. Forward mean draft is equal to portside forward draft plus starboard forward draft divided by 2. The result is 8.33 meters. For the aft mean draft, use the aft draft, port and starboard, but in this scenario, we have the same draft on both sides, so no need to do this procedure because we got the same value. The aft mean draft is 10.17 meters. For the midship mean draft, use the midship draft, port and starboard. The midship mean draft is 9.24 meters. Remember that these drafts are taken by visual observation of the ship's draft marks. Here are the starboard drafts: forward draft, midship draft, and aft draft. The corresponding portside drafts are located on the opposite side of the vessel. Let's proceed to the second step, which is to calculate the apparent trim. Take the difference between the forward and aft mean draft. The apparent trim is 1.84 meters by the stern, since aft mean draft is greater than the forward mean draft. Let's proceed to the third step. Calculate the P correction or perpendicular correction. These are the formulas. Let's start with the correction factor. Assuming the ship's forward perpendicular is here, the after perpendicular will be here, and the midship is here. In our given, the forward correction factor is 1.48 meters. If this is the ship's forward draft mark, the horizontal distance between the forward draft mark and the forward perpendicular is 1.48 meters. The reason why we need to calculate the forward P correction is because we need to determine the forward mean draft along the forward perpendicular. Now for the aft draft mark, the horizontal distance from the after perpendicular is 6.93 meters. To determine the aft mean draft along the aft perpendicular, we need to calculate the aft P correction. But in the case of the midship draft, the correction factor is 0, which means that the midship draft mark is along the midship, so there is no midship P correction. The correction factors are provided by the ship builder. We can usually find it in the ship stability booklet. Now the horizontal distance between the forward and the aft perpendicular is called length between perpendicular, LBP. And the horizontal distance between the forward and aft draft marks is called length between draft marks, LBD. Length between draft marks is needed to calculate the P corrections, and this can be found in the ship's particulars. The given LBD in this scenario is 159.46 meters. In this scenario, the forward P correction is 0.017 meter. And the aft P correction is 0.080 meter. In the next step, we will determine the corrected mean draft, or true mean draft, by applying the P correction and if applicable, the keel correction. While some vessels require a keel correction, in this scenario, our ship does not, so we will only apply the P correction. These are the rules for applying the P corrections. Our ship is trimmed by the stern, so this is the applicable rule. By subtracting the forward P correction to forward mean draft, the corrected mean draft forward is 8.313 meters. And by adding the aft P correction to the aft mean draft, the corrected mean draft aft is 10.250 meters. The midship mean draft remains the same since there are no corrections. Next, apply the keel correction if there is one, but in our scenario, no keel correction, so the corrected or true mean draft forward is 8.313 meters. And the corrected or true mean draft aft is 10.250 meters, and the midship mean draft is 9.240 meters. The next step is to calculate the true trim. This is done by taking the difference between the corrected mean drafts, forward and aft. The true trim is 1.937 meters. Next, calculate the mean draft. The formula is mean draft is equal to corrected mean draft forward plus corrected mean draft aft divided by 2. The mean draft is 9.2815 meters. The next step is to calculate the mean of mean draft. The formula is mean of mean is equal to mean draft plus the corrected midship mean draft divided by 2. The mean of mean is 9.26075 meters. Next step, we will calculate the quarter mean draft. The formula is quarter mean is equal to mean of mean plus the corrected midship mean draft divided by 2. The quarter mean is 9.250375 meters. In the next step, we will use the quarter mean draft to determine the ship's displacement. Longitudinal center of flotation or LCF, and tons per centimeter immersion or TPC from the hydrostatic table. This is our ninth step. Let's use the quarter mean draft value of 9.25 meters since this exact value can be found in the hydrostatic table. Later on, we will deal with the remaining draft increments to find the corresponding additional displacement. So at a quarter mean draft of 9.25 meters, the ship's displacement is 29165 metric tons. The TPC is 34.47 tons. And the LCF is minus 0.98 meter. Now let's calculate the additional displacement for the draft increments. We are supposed to find the value of the ship's displacement at a quarter mean draft of 9.250375 meters, but we only got the value of displacement at a draft of 9.25 meters. To do this, let's take the difference to get the draft increments, which is 0.000375 meter. Then multiply these draft increments by 100 to convert into a unit of centimeters, since 1 meter is equal to 100 centimeters. Next multiply the draft increments in centimeters to TPC, which is 34.47 tons per centimeter. This is the reason why we convert our draft increments from meters to centimeters. So the displacement correction for the draft increments is 1.29 metric tons. By adding this correction to the displacement at a quarter mean draft of 9.25 meters, the ship's displacement at a quarter mean draft of 9.250375 meters is 29,166.29 metric tons. The displacement correction looks like too small, but if the draft increments is greater with a greater TPC value, the displacement correction might be greater than 50 metric tons. This is the reason why I did not go through any linear interpolation for the value of TPC and LCF, since the draft increments is too small. If we do some interpolation, and round off to 2 decimal places, we get the same value. You might be using a different method of finding the displacement correction. The procedure I've shown serves only as a guide. Let's proceed to the next step. Calculate the first and second trim corrections. This is the formula to calculate the first trim correction. The true trim is 1.937 meters, the LCF is negative 0.98 meters, the TPC is 34.47 tons per centimeter, and the length between perpendicular is 167.87 meters. By multiplying 100, we convert centimeters into meters. The first trim correction is 38.98 metric tons. But remember that we have the rules to be followed for the first trim correction. If the ship is trimmed by the stern, follow the LCF sign. And if the ship is trimmed by the head, reverse the LCF sign. Since our ship is trimmed by the stern, our first trim correction is negative 38.98 metric tons. For the second trim correction, this is the formula. Our true trim is 1.937 meters. 50 is a constant value. The LBP is 167.87 meters. For the moment to change trim by 1 centimeter, MTC difference, let's deal with it. To determine the MTC difference, extract the value of MTC from the hydrostatic table at a quarter mean draft plus 0.5 meter, and at a quarter mean draft minus 0.5 meter. So at plus 0.5 meter, the quarter mean draft is 9.75 meters, and the corresponding MTC is 241.2 metric tons. And at minus 0.5 meter, the quarter mean draft is 8.75 meters, and the corresponding MTC is 225 metric tons. The MTC difference is 16.2 metric tons. The second trim correction is 18.10 metric tons. And the rule for second trim correction is always add. We add and subtract 0.5 meter to the quarter mean draft to account for how the moment to change trim varies at slightly higher and lower drafts. This allows us to determine how the MTC changes across a small range of drafts. Since MTC values vary with draft, calculating the difference between the MTC at these two nearby drafts gives us the rate of change in MTC over a 1 meter draft range. This difference is important when performing trim corrections, as it reflects how much moment is required to change the ship's trim across the current draft range. For our next step, we will apply the first and second trim corrections to our displacement value at a quarter mean draft of 9.250375 meters, which is 29,166.29 metric tons. By subtracting the first correction and adding the second trim correction, our displacement corrected for trim is 29,145.41 metric tons. This displacement value that we have extracted in the hydrostatic table is given when the ship is floating in salt water, so this displacement is in salt water. However, since our ship is loading cargo in dock water, with a relative density of 1.017, our next step is to calculate the ship's displacement in dock water. And the formula is, displacement in dock water is equal to displacement in salt water times the relative density of dock water divided by the relative density of salt water. Remember that the displacement in salt water being used is the displacement corrected for trim. The ship's displacement in dock water is 28,917.93 metric tons. This is also the displacement corrected for density. It represents the actual displacement of the vessel, calculated from the given observed draft after applying all necessary corrections from the beginning of the calculation. Let's proceed to the next step, calculate the deadweight. Just subtract the lightship, or lightweight from the ship's displacement that have been corrected for water density. The difference is deadweight. Lightship can be found on the ship's general particulars. So the deadweight is 22,242.93 metric tons. As we know, deadweight is the total weight of everything the ship is carrying at a given draft, whether fully or partially loaded. It includes cargo, fuel, water, stores, crew, and passengers, regardless of how much of the ship's capacity is being used. Even if the ship is not fully loaded, the difference is still called deadweight. To find our cargo being loaded, we should know our deductibles on board, such as ROB and other known weights. In our scenario, the deductibles are fuel oil, diesel oil, lube oil, ballast, and fresh water. The total deductibles is 1,632.41 metric tons. If we subtract these known weights from the deadweight, the difference represents the cargo being loaded, along with the constant, which totals 20,610.52 metric tons. Take note about the cargo being loaded on board and the constant. During the initial survey, where the ship has no cargo, and she is in ballast condition, the difference is the constant of the ship. While if the ship is in loaded condition, the difference is the cargo being loaded on board and the constant, just like in our scenario. Let's assume that during initial survey, where the ship is only in ballast condition, the ship's displacement corrected for density is 8,627.41 metric tons. If we subtract the lightship, the deadweight is 1,952.41 metric tons. Assuming that our deductibles remain the same, which is rarely happened. The difference is the ship's constant, which is 320 metric tons. It means that we can determine our constant during initial survey. If we subtract the constant here, which is taken from the initial survey, the difference is cargo that has been already loaded on board, which is 20,290.52 metric tons. If no more cargo is to be loaded, then we will be sailing with this amount of cargo on board. But in our scenario, we have a booked cargo. As per the charterer advice, we are going to load 32,000 tons of cargo. The difference between the booked cargo and the cargo that has already been loaded on board is the remaining cargo to be loaded, which is 11,709.48 metric tons. This is the amount of cargo to be loaded to hit the target of 32,000 metric tons. Now the 13th step in our procedure is also the last step, which is calculate the deadweight, cargo loaded, and cargo to be loaded. That's all for now. I hope you found this video helpful. See you in my next video. Thank you for watching. Bye.